Okay, so welcome everybody. Good morning. So again, I'm Casals. So here are some suggested rules of engagement, which is number one, you can and you're absolutely welcome to interrupt me at any point. So I'm essentially yours 9 to 5 p.m. every day. But during the talks, like you're also welcome to interrupt. So ask questions of any sort. Questions can range from, hey, here's this very technical detail I don't understand, can you please expand? To do another example, to, hey, I've heard this word related to this, can you say something? And, I'll make the call of whether I should, say something in the lecture or just like do it afterwards. But any question that you are asking is really helpful, not just to you, but to sort of everybody. So I am writing some notes on this, so I'll mention these in a second. And any questions that you have, inform me about what kind of things should go in the notes, because I'm not thinking about this, okay? So not just for yourself, you're doing that for maybe people in the years to come. Okay, and then the second thing is in my website, so you just Google my name, there's a little section called CBMS, and in there is a link to some notes. So those notes cover reasonably thoroughly the first 5 lectures. And so if you're at any point feeling lost or you need a reference or where do I read that, like more precisely, the notes are there for you and references therein. And then, yeah, so please, it should be trivial to find these. Again, Google my name, just go to the CBMS section. Right. And then if there's any questions on the notes or suggestions, you can also just tell me about it. Now, yeah, so what are we trying to do here? What am I trying to convey to you? So there is this geometric problem about studying Legendrians and maybe also studying Lagrangian fillings of Legendrians. And the first lecture right now is going to be purely on that geometric problem. The word sheaf is not going to appear, but I mean, it tends to be extremely useful to understand the geometry very well before you try to do any algebra about it. So always keeping the geometry in mind, we will, throughout the course of the lectures, introduce sheaf theory and kind of motivate it through that lens. The notes have other uses of sheaf theory. There's no claim whatsoever this is the only way to do it, but that's it. And then the last two sort of quick disclaimers is the first one is the theory is extremely general. There's a beautiful book by Kashiwara and Shapira, read it 30-something years ago. And the nodes are written rather generally. So for any manifold M, the coefficients is like any symmetric monoidal, compactly generated infinity category, so on and so forth. None of this is going to be mentioned in the talks. Okay, the talks are going to be down to earth, R2, R3. If any try to mention anything else, it's going to be very, very down to earth and explicit. Okay. The idea is that you understand the points through the basic examples that really motivate us. That's the thing we imagine in our heads. And then when you want to use the powerful machinery, then you have the notes to say, yeah, that this is the theorem, this is the reference, so on and so forth. Are we okay with that? Okay. All right. So I'm gonna start talking about Legendrians and Lagrangians right now, and just so we're all on the same page, I'm gonna start talking about contact and symplectic manifold. So here's the setup that we are going to have. So we'll focus on the following smooth 4-dimensional manifold. We're going to consider the space T star of R2. R2 is going to be endowed with coordinates Q1 and Q2. And we typically draw these as a horizontal plane like this. There is going to be a reason why I'm doing all of that. And in the sheaf lectures, you're going to see that. The typical picture that sometimes you see me do in talks or in the intro of a paper, it's something like that. There's a round 4-ball, and then I'm studying the Legendrians on the boundary and fillings inside of it. That 4-ball is essentially very close to this space, essentially symplectomorphic. Okay, so I'm going to consider this cotangent bundle, and the coordinates in the fibers are always going to be P1 and P2. So as a smooth manifold, this is diffeomorphic to R4, so there's no kind of surprises in there. But when you write it like that, it has a very natural symplectic structure. And the symplectic structure is, for instance, written as this. You can write it as P1, DQ, let's see, DQ1, DP1, DQ2, DP2. All this is saying is whenever you're at a point, you're in a 4-dimensional space, maybe you're measuring the 2-plane field, then the way you're going to measure the area of this 2-plane field is you're going to project it down to Q1, Q2. It's going to give you some blob. You compute that area. Sorry. Let me do this. So this is P1 and P2. So you project to the P1, Q1 plane, it's going to give you some blob, you compute that area, and then you project to the Q2, P2 plane, it's going to give you maybe some blob, you compute that area. Now, it is possible, for instance, to have a plane, a two plane in 4D that projects to a line and a line. So it shouldn't be surprising at all that things have area 0 sometimes. They might have negative areas, okay? So this is the way we're going to compute areas. And this guy actually, purely from a differentiable viewpoint, it has a primitive. This is called the Liouville primitive. And it's going to be given by minus, and then P1 dQ1 plus P2 dQ2. So this is often known as the Liouville form. And if you want to think of it a bit more dynamically, you can think of the dual vector field under this. And what it's doing is that every fiber is expanding radially out. Okay. So the dynamics of this at every fiber 0, 0, it's doing this. And it does nothing to the Q variables because there's no dP2 nor dP1. Okay, so when you dualize, you're not going to have any partial Q1 or partial. Are we comfortable with this setting? So this is the ambient 4 manifold in which I'm going to do all my computations. Now, inside of this 4 manifold, there is a space which is going to be denoted T infinity of R2. And it's just going to be given by the subset of all those P's such that the norm is equal to 1. Now, this is not ideal in that you have to choose a metric in order to name that space, and maybe, you're allergic to extrinsic choices. That's fine. You can go two ways about it. You can say, well, whatever I'm going to do here does not really depend on the metric, and the choices of metric sort of are contractible with respect to that. Or there's a better definition of an ideal Liouville domain, and this is the ideal contact boundary, which never mentions the metric. So there's a way to do that. The notes sort of provide references for that. Now, what is this smoothly? Smoothly speaking, there's nothing sort of fancy happening here. It's just the standard R2. And now in each fiber, which is this R2 with P1 and P2, you just take the sphere. And so in here, I can take theta, and this theta is going to be exactly the theta that gives P1 and P2, but in radial coordinates. So this is going to be cosine of theta, sine of theta. Are we okay with that? Now, in the same way that this had a geometric structure, a way to measure area, and it had this primitive, this also has a geometric structure induced by that. And so when I take these green piece in particular, this one form, and I restrict it here, it gives us what we call the contact structure. So here, the standard contact structure is going to be, by definition, the following. It's going to be the kernel of that Liouville one form restricted to this boundary, the infinity of R2. So what is this? Well, when I write it in coordinates, I can write it as the kernel of, now I can do cosine theta dq1 plus sine theta dq2. And all I did was take this formula and substitute the P1 and P2 by cosine and theta and take the sine because it's a kernel. So what is happening here is in this manifold, at every point, you have this linear form defined, this linear equation at every tangent space. And so when you put it equal to 0, it gives you a two-plane inside a three-dimensional space. And that has certain properties, which is subsumed by the fact that this is a contact structure. And the properties precisely mean maximally non-integral. But for now, we don't really need to care about this that much. We just need to know that there's this two-plane field, and it will have properties that we will use. But we don't need to be implicit about it. You can just say it's exactly given by this equation. We're going to use this equation. Are we comfortable so far in this setup? Okay. So first, quick comment for experts and non-experts, for everybody. There's sometimes this business about, well, T infinity of R2, so this kind of R2 times 1, versus like R3. And the issue is, there's two kind of R3s that are often used in the literature, and they're kind of different. So I wrote them in that blackboard over there. So one thing is, around any point in this manifold, there is a smooth a smooth 3 ball. So really smoothly nothing, a little neighborhood. And then the contact structure restricts to that open ball to a contact structure. That happens to be contactomorphic to what we call the standard R3 psi ST, which is like dz minus y dx. For instance, as an example, if here I happen to never choose the angle theta equals pi half, then cosine is never 0. So I can move the cosine to the other side and I get dq1 plus tangent dq2. But in these angles, this is a coordinate on itself. So I can rewrite this as dz minus y dx. So for instance, away from theta equals pi half, or really any angle, then you recover the standard Darboux ball. All right. So that's one use in which you can say, well, I'm going to study Legendre and whatever I do in a Darboux ball. So something that really doesn't go through all the angles. That's one way the literature explores this problem. Now, a second way is once you're here, you can say, well, it's a bit odd, right? Because like if this is to be thought of as R4, as a 4 ball, its boundary should be a 3-sphere. But here I'm only seeing a solid torus in a 3-sphere. Where is the other solid torus? And one way to implicitly talk about the other solid torus is to, which is this picture over here, is to satellite this fiber in here, this S1, as the standard unknot in S3 or in R3. And then now you have this guy inside something that again is a Darboux ball. They're both used a lot, they're both very useful, but just be careful. If anyone is talking to you about Darboux balls or R3s, just ask them, are you talking about the one it's kind of inside or after satelliting? And the satelliting has a choice. I chose the unknown because of the picture of the S3, but there's other choices. Lenny?
Yeah, so for this first picture, you said you just cut out one particular value of theta. That can't be right? Or at least not the way that you said, because cosine being 0 has 2 solutions. You actually mean T infinity minus or
So what I said about the R3, really you have to avoid two angles. But I mean what is absolutely true is that around any point there's a little ball, and in that ball that's conjecturomorphic to that. Okay? All right. So this is the geometric setup of the ambient manifolds. Now, if you care about other manifolds, 4 manifolds, or 3 manifolds, you can take these guys and actually embed them in there. And so anything you want to care, anything you're going to study, you're going to have to go through these. So any phenomena that's happening here that's already surprising will happen in more general manifolds. So that's the first comment. The second comment is, now that I'm going to introduce Legendrians and Lagrangians and all, you can perform operations to them in these manifolds, such as surgeries for the Legendrians at the boundary, or handle attachments for the synthesizer will create 4 manifolds that are very interesting, and same with 3 manifolds. So again, understanding that it is useful in more generality than just this set on its own. Okay, are we okay so far? All right, so first definition, that's the main object of interest, one of the main objects in these talks. So a knot, or a link in general, so a link lambda inside of the infinity of R2 with this convex structure standard is said to be Legendrian, so that's a smooth link, is Legendrian if its tangent space is contained inside this distribution. So remember, at every tangent space, this was a 2-dimensional plane, so this was a 2-plane inside of the tangent space at a given point. That's just T of this the infinity of R2. So this is a 3-dimensional space. This is a 2-dimensional space. The knot is 1-dimensional. You're asking that this 1-dimensional space actually always lies in this 2-plane. Okay. Now, this is a definition we use, but in practice, we're going to have other things. So this is something that's happening at the boundary. This is something that's happening in here. Now, what is the analog inside? So inside, we're going to have the notion of Lagrangian, a surface L inside of the star of R2 is Lagrangian if omega, the standard omega we have, when you restrict to it, is 0. One way to think about it is, at least locally, the areas that you're going to compute infinitesimal are 0. And an example would be if something projects to a line in the plane Q1, P1, and something projects to a line in the plane P2, Q2, then you're done. It doesn't have to be a line, it could be a curve, like a circle and a circle. That will give you a Lagrangian. So these are the main 2 objects of interest for us, the Legendrian in here and the Lagrangian inside. Again, the picture to keep in mind is the Legendrian is outside in this T infinity of R2 that you think of as the boundary of this. Boundaries of this bundle to be precise. And then the Lagrangian is the orange surface depicted inside, and the idea is that this is going to bound this. Okay, so I'm going to write this in red. So theme is going to be that the boundary of L is going to be restricted to be lambda. And questions that you can pose is, given a lambda, do there exist such L's? how many, how are they related, so on and so forth. Okay, so this is the main definition. And now we need a couple of comments with respect to what do we mean by equality. So the notion of isomorphism in this context is as follows. We're going to say that two Legendrian links are Legendrian isotopic, informally the same, if there exists a family of Legendrian links that starts at one and ends at the other. So lambda 0 and lambda 1 are Legendrian isotopic if there exists a family lambda t, where t goes from 0 to 1, such that at every point t, that is a Legendrian link itself. Are we comfortable with that? It needs to be a smooth embedded link. Similarly, a Lagrangian, we're going to have the notion of Lagrangian isotopy. So two Lagrangians are going to be Lagrangian isotopic if there exists a family interpolating from one to the other, right? So now a couple of technical comments. So these are important, but sort of slightly more refined than this. So L is said to be exact. This is a definition. L is exact if not only does omega vanish, but actually the primitive of omega also vanishes cohomologically speaking. So when you restrict this to lambda, it is of the form df for some f, which is to say, i.e., the class, the cohomology class of lambda restricted to L in the RAM cohomology is 0, because it is closed because of this property by being Lagrangian. So L is Lagrangian, that means it's closed. It's actually 0 means it's exact in here. Right? So that's kind of a cohomological condition. Doesn't never mention the F, but it's listen to the RAM. Okay. So we're typically going to care about exact Lagrangians. So that's the first thing to be said in here. And then two exact Lagrangians are going to be set exact Lagrangian isotopic if there exists a family of exact Lagrangians going from one to the other. So maybe some comment that's worth writing down is that L0 and L1 are exact Lagrangian isotopic, that I just described, exact Lagrangian isotopics, if and only if they're Hamiltonian isotopic. So if you don't know what Hamiltonian isotopic is, great, you don't need it. But if you did know and you're like, you never said this very important word, that's actually very classical isotopics. So L0 and L1. Okay, so those are the two remarks. Are we all right? Goals, starting goals are given a smooth link, can it be made Legendrian? If so, in how many ways? Given two Legendrians, how can I tell them apart? How can I say they're equal? Same with a Lagrangian. So, and then here in this situation, when we have a Lagrangian L coinciding with lambda at infinity, we're going to say that L is a Lagrangian filling of lambda. Now, for experts, and the notes are precise about that, you need slightly more than that. You need a slightly color neighborhood. It needs to coincide with the cone, and then something about the primitive being constant. But essentially, the geometric picture is the boundaries there. Lagrangian filling. Oh. All right. Are we happy with like all the basic words? Okay, so now a little rant on myself. I never see anywhere in the literature that somebody pointing out that in fact this is a highly non-generic condition. So actually, Lagrangians intersecting contact hypersurfaces in Legendrians, it is not generic. It is a dimension 1 condition. So when you go around talking to maybe smooth GNT people, the Lagrangian intersecting the Legendrian, that almost, open doesn't happen. Like it's a very special thing. But we do choose that, and there's a reason why we can do that so on. All right. So we're going to study that. There's a remark in the notes about how to make that precise. So these are concepts which are very classical. They originated, some of them, in classical mechanics. So Joseph Louis Lagrange, so that's like 1750s, 1760s, so on. That's the one who introduced sort of mechanics from a viewpoint of Lagrangian mechanics, Hamiltonian mechanics afterwards. And he wrote this treatise in 1788 called Mécanique Analytique, so analytic mechanics, that was aiming at explaining physics through the lens of sort of mathematics, variational calculus, so on and so forth. And it's really interesting if you go to math genealogy and follow Lagrange descendants. It's like Lagrange, Poisson, and then Chasselet, and then you hit like the big one. So there's like Cartan, so on and so forth. So there's a very nice, beautiful math tree. And then at the end, you start to hear names you might be familiar, like Jan Serve, Francois Lodenbach, Claude Viterbo, And then, oh, okay, okay. They didn't just come out with that recently, like really a long time ago. Any locals should be maybe fond of this date. What happened in 1788? Georgia ratified the Constitution, becoming the fourth state. Where is oldest Georgia when it comes to studying concepts in math? Okay, is this thing clear so far? Okay, so now let's do examples of these things. So how do we think about them? If you think in terms of knot theory, how do I think about a knot in R3 or a knot in S3? It is common to use diagrams. So you will take a knot and project it into some plane, for instance, and you're going to see this diagram generically. Now, fundamentally, it is a two-dimensional data plus the extra choice of whether the crossing is like up or down. But that extra choice is kind of really tricky to keep track of. So knot theory truly is kind of like three-dimensional. Like you cannot really just think about a plane with a diagram where the crossings are not specified. And it's not that you just have to specify one Z-mod 2 piece of data. It's like a lot of them and they interact in interesting ways. Luckily, this doesn't happen here. So there is a notion of non-diagrams. And the way this goes is that you have maps from both these manifolds down to the base Q1 and Q2. So here you would say the projection onto the zero section. And so let's write pi for the projection from this R2 down to R2, where we forget about the coordinate P1, P2, which is this theta coordinate in here. And that allows for any knot happening here to project down. Now, how it will project? Well, it will project in something that looks like that. It just depends. And now you say, well, in knot theory, I would have to specify the crossings here, 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 so on and so forth. And the answer is, well, yes, but think about it this way. If this is a curve parameterized by like gamma t, so this is Q1 of t, Q2 of t, now the only variable that you're missing is theta. So how do you get theta out of that? So theta t is recoverable from this data. Essentially, it's a partial derivative. Why? Well, look at this equation. How can you think about this equation in here? You can think of this equation as cosine theta, comma sine theta, dot product, kind of dq1, dq2, right? Are we okay with that? So if you have the equation that this must be zero, because this is the kernel equation in here, the kernel here translates into this being zero. Now, up to choosing the sign of theta, so there's this ambiguity, but up to choosing the sign of theta, if I have the partial derivatives with respect to the first and second coordinates, so if I have the velocity vector of here, you have this velocity vector in here, the Legendrian condition, which is this one, will uniquely specify one theta up to sine. Okay? So in general, any immersed curve, look, at this immersed point, I didn't care about that. Why? Because at an immersed point, both velocity vectors are both velocity vectors are different, so this point will live to two different points upstairs. Okay? So any immersed curve lives uniquely to a Legendrian as long as I specify a co-orientation, because the hypersurface is the same as the orientation. We're going to indicate co-orientation by a little hair like that. And all it means is, in here, I would have two choices of conormal, orthogonal to this vector, and I choose the one that's with the co-orientation sign. Does that make sense? So a very, very, very important class of Legendrians, essentially any Legendrian arises that way, is through an immersed curve. Now, because we only cared about first derivatives, there's a second thing you can do. You can, for instance, add a cusp in here. And if it is a simple cusp, so ask for this cusp to be simple. Simple means it's locally modeled as x squared equals y cubed instead of, say, y5 or something like that. Then the derivative will also exist. So there is still a tangent plane in here. So it does make sense to lift this. Again, the point is the simple cusp has a well-defined tangent space, and so it does lift. So any immersed curve with a cusp actually lifts to a Legendrian. And now it is a lemma that you can prove that any Legendrian upstairs generically will map to something that looks exactly like that. So an immersed curve in the plane, possibly with cusps. Are we okay with that? So that is the contact analog of a knot diagram. Now, when you see these cusps, you're like, oh, it's something singular. No, it's not. There's nothing singular about a cusp. famous last words. But, okay, I know. So this was happening in a Rademacher one move. In a Rademacher one move, you have this guy, right? Everybody see? Okay, Rademacher one. Okay. Everybody's happy with that? That's smooth Rademacher one. Okay. Now stop right at the moment where the critical phenomena happens. Stop right here. What does your eye see? It sees exactly a cusp. So if I had a flashlight and I project it on the wall, you would say, oh, it's a cusp, oh, it's very singular, I'm gonna get pointy. No, there's nothing pointy about it. Very nice smooth point, it has tangent vector, so on. That's what's happening. It's just the contact geometry, this condition forces you to exactly project your eye to deal with exactly from that point. That's the only thing. But a perfectly nice, smoothly upstairs. Okay, quick comment for experts. Notice that there's an homology class here. If you just have some high winding number, I mean, that's going to be a non-trivial homology class upstairs. But you can perfectly find here, draw your usual, the loft knots like this, your propagation downwards. That lifts to something upstairs that avoids enough angles, and now you're in the blue ball on the left. So you can just do the standard. Does that make sense? So every beloved paper in R3 fits into this set. It's just it's when the angle doesn't go all around the fiber. You know, homological untrue. Are we happy with this? Okay. Okay. I'm gonna pause for a second. Any questions at this stage? Yeah.
Does the beloved R3 picture correspond to some canonical choice of the conormal in that picture? Like, is there a recipe for doing that translation?
Not canonically.
Okay.
No, I mean, I could have chosen the orientation outwards, like upwards, to the right, to the left. I could have chosen to avoid several angles. There's no canonical kind of the blue ball inside. There. Are we happy? Yeah.
I just wanted to clarify. So you said like once you choose a conormal or like orientation,
Yeah.
then because like before you had this like issue where there's like two thetas you could live to, like plus or minus.
Yeah.
But when you choose a co-orientation, you fix one of those.
Yes, exactly. So the orientation is telling you which of the two you're going to lift. It's just you literally have two choices, and the orientation is just a pictorial way. I mean, it's a concept, right? But when we draw the hair like that, it's a pictorial way to say it's this theta, not the other. All right.
Yeah, so regarding the exact Lagrangian feelings, I was wondering why do you need the condition of like the exactness?
Right. I mean, the short answer is because otherwise this is a very different problem. So the classification is no longer the expected way discrete. You have continuous families. For instance, if you choose a circle here and a circle there, then the area of that circle in Q1, Q2, which is not the subjective area, that does matter. So you could have this kind of continuous family of interesting tori in R4, none of which are exact. So the short answer is it's a slightly different problem than that. And for now, we focus on that. There is a sense in which they are related. Okay, any other questions? Okay, so before I start drawing stuff, I just want to make a quick comment that this is what we call a front projection. Front projection is another word for Alexandrian fibration. What this is saying mathematically, when we call this a front, is saying that the fibers are Legendrian. So that means the fibers are Legendrian. And indeed, if I fix Q1 and Q2 in here, dQ1, because Q1 is constant, is 0, dQ2 is also 0 because it's constant, so the whole thing is in the fiber. So in this particular splitting, any such as one is a Legendrian. And then any front is allowed, you can draw any front as long as you have a Legendrian projection. And it doesn't matter which one you choose. As long as you have a Legendrian projection, you can run this machine. For non-arbitrary contact 3 manifold, it's kind of tricky to get a Legendrian projection. You might want to use open books for that. So, all right. Okay, let's do tons of examples. So, one thing that's very useful about these diagrams is that you can just like draw inverse curves. And then, of course, the question is, if the two inverse curves that I just drew coincide or not, are they Legendrian isotopic or not? If they are, how do I see that? And if they're not, well, how do I go about that? So let's do a bunch of examples here. And again, comments you can make are, this is too easy, please, ramp it up, or no, this is too elaborate, please go down and. Okay, so I'm gonna start with examples like this one. So this is something that I draw in the Q1, Q2 plane and always oriented downwards. So whenever I pass a cast, the orientation doesn't change. So that's an example in here. Another one that I can draw is something like that. Again, oriented downwards. So smoothly, this is an unknot. Smoothly, it's an unknot. And it's an unknot in the sense that it's an unknot in a 3-ball. That does not, is topological trivial unknot. Okay, in here. So that's what you would see if you do that. Now, a priori, you wouldn't know that this is equal to that. I mean, many of you in your brains have ingrained that this is obviously a randomizer rule. We don't know that yet. So a priori, this would be some other Legendre, which you would know it's the unknot, but now you want to argue that smoothly, not just smoothly the unknot, also Legendre wise, the unknot. Okay. Now I'm gonna get a bit funky. So let's choose the circle like that, oriented inwards. And we can also choose the circle oriented outwards. You can also do something slightly funnier, which is we can choose a point. So this is a point, for instance, the point Q1 equals to Q2 equals 0. But we now not only specify one orientation, but we specify a bunch of orientations. They go up all these little pairs like that. So this little sunshine Legendre in here, it's saying it's something that maps to this point, but the angles in which it maps, it's all the hairs possible in here. Okay, so questions. Are these guys related to each other? So these guys actually will turn out, I'll talk about it in a second. This will all turn out to be Legendre and isotopic to each other. And one intuitive way to think about it is you can collapse this guy until it becomes a point. So this collapses to this, and then you open it up that way. So it's a very highly non-generic isotopy, but it's a perfectly fine isotopy. Are we okay with that? All right. So that, and you can continue to draw like interesting curves in any ways that you like. So for instance, you could draw this one, you could draw more complicated things like this one. And now just the more classical depictions of Legendrians, you could draw things like this, or this. And there's also perfectly fine to do Legendrian links. So if I don't draw orientations, by the way, they're always downwards. The convention is the hairs always go down. It's expansion. So this is an example of a smooth half link that lives in a Nerveau ball, which is realized to Legendrian. Another example is this one. And another example is this one. So these are all of them 3 smooth half lengths. If it's apparent to you that they're smoothly the same, which might not be, and that's something to think about for a second, are they Legendrian the same? And we will go. So then we will continue. Okay. Are we happy with this picture so far? Is it clear what's happening? These are pictures drawn in Q1 and Q2. You could technically parameterize these things, and then you will leave the theta according to the only theta that satisfies that with that given orientation. You happy? Okay. Quick note for the experts. If you satellite S1 along the unknot, these, and these do become this. This first one becomes this one, and this one becomes this one. So in T infinity of R2, this guy and this guy are not related. Neither are these or these, because this is homologically trivial and this is not. It's classical one-round fiber. But once you satellite the fiber, so if you think really about the S3 picture at the boundary, then this, by definition, the fiber gets satellite to the unknot means this gets satellite to that. And a slightly more interesting statement, when you satellite this guy to this, then this guy also becomes that, and actually this guy becomes the trefoil. So if you ever see me or somebody writing in a paper, this is the trefoil, it's wrong. Okay, it's not a trefoil, it has a non-trivial homology class somewhere. But once you satellite after S1, so if you hear something like this, the trefoil or something like that, always keep in mind they're satelliting automatically along. That clear? All right. Questions on the pictures? Do you want me to draw more pictures, less pictures? All right. So let's address the question of how do we tell if they're the same? And in the second lecture today, we will start addressing the question of how do we tell if they're different? Okay. The typical philosophy here is you talk about construction of isotopies. So you want a constructive theorem that says these two guys are the same, you're gonna leave, here's a set of moves that do the job for you. And the obstruction part is usually find some kind of invariant oval Legendre isotopy, such that you can compute for both guys, and if these guys are different, the invariants are different, then the Legendres themselves are different. Are we all happy so far? All right. So first statement, classical Rademacher theorem in the Legendrian setting, giving you conditions for these guys to be the same. Right. Theorem. This is known as the Legendrian Rademacher theorem. Legendrian Rademacher. So there are references in the notes. You can see the exact paper and everything. I would strongly encourage you to just open the book Singularities of Wavefronts and Caustics by Arnold. And everything is drawn there in beautiful pictures and tables, and not just in 1D, 2D, 3D. So you can see the general pattern that these kind of things follow. So on the zero is Legendre isotopic to lambda 1. So this isomorphism means Legendre isotopic to lambda 1, if and only if the front diagrams, so pi of lambda 0 and pi of lambda 1, are related by the following moves. And the moves that I'm going to describe now usually are called R1, R2, and R3. The first move is every time I have an arc oriented downwards, I can insert a cusp like that. This is the smooth analog. So smooth is the Rademacher 1 move. This is the Legendre analog of that. The second thing is any cusp in here, if you want to pass it through a line, you're just gonna pass it through as is. Interesting stuff in there. Analog of the Rademacher 2 move. By the way, people on the south, in there, like if there's some word that I should never write because it's too down, just tell me. Is this okay still? All right. So the Rademacher 3 move sounded like that, and those are the ones that usually are taught. I mean, I cannot count anymore how many students keep referring to John's notes on the Legendres and transfer notes. So I assume this is the canonical reference to every. Oh, I learned it from John's notes. Okay, so these are definitely John's notes. So something that's not in John's notes though is because he doesn't cover this R infinity setting. There's also another move which I'm writing here kind of on the side, which is the following move, and it's not a clasp move. It's what Arnold called a non-dangerous tangency, which is when you have two people co-oriented outwards, then you can actually do that. Okay, this is not a class move. The class move is they're both down, and yet you still do that in your brief. No, that's not what's happening. Every move in here has its symmetric version, orientations upwards. This guy is grown downwards. This is flipped like that. So it's these moves and all their things. Okay, so usefulness of this theorem. Well, if you suspect these two guys are isotopic, forget about the 3D setting, just start playing with the front diagram. So these here are the fronts. And that becomes really the art of what I call front cooking. You just go and start to like play with things, and it's kind of amazing. I don't know if you've ever seen Dan or somebody like do Rademacher moves in the front. It's just a beautiful thing to do. It's a lot of fun. Now, it might be that you don't succeed. That doesn't mean, they're not isotopic. It just means it's easy to find. And sometimes they are pretty tricky. Anyway, so applications of that theorem, these two are Legendre isotopic in here. Now, that theorem has a beautiful application, which is it relates how these two guys are related. So this is actually something that appeared in the front page of the New York Times. You don't see Legendrians in the New York Times often. They're very political about it. But here's something that happened. So there was a volcano in Tonga, and it exploded, and it created this big seismic wave. And the way the wave went is, it expanded from the volcano outwards on Earth. And they have, the New York Times article has like the wave expanding and everything. And then it reached the other antipodal point of the volcano, and something happened. And then it continued kind of the other way around. now with the orientation flipped. Now, naive scientists in the world said, oh, what happened is this, it went down like that, and then this happened. But then there was a guy in Islas Baleares, a marine biologist, who actually kept track of the seismic waves very carefully and said, no, like you're not just seeing the point, you're seeing a more refined kind of version of this. And of course you are, because the point is not a generic thing. So this is what's happening in general. What's happening in general is this guy is going inwards, and eventually it develops two cusps like this. So it's this kind of like candy, you can think of it as this candy. So these two Rademacher moves are created in there. Now, when this, so think of it as a Rademacher move here and a Rademacher move there. So these are like here. So this like this is a bit for kids, but okay. You have this. Now, at this point, so this is a Rademacher 1 move. Now you can use this move in here, the non-dangerous tangency, and separate this candy thing. So the non-dangerous tangency gives you this beautiful asteroid in here. The 4-pointed asteroid in there. Are we in agreement with that? It's pointing outwards in here. And now what has happened is we've undone this one, but now these two come in together. So now, while keeping the ones above, now the twist happens kind of. The twist happens in this vertical direction. Does that make sense? So now, before it was these two guys opening up, and now it's like these two guys coming in while these two guys keep going outside. So you get to this one, and then at the end, you undo the Rademacher moves, and you get to that one, and it's now correlated outwards. So this is 2 times 1, 2 times R1, and this is 2 non-dangerous tendencies done in the different ones.
The hairs on the asteroid, the top of the bottom.
Yeah. Yeah, that's. Oh, perfect. And then. Well, the way I drew it, but it's just an example of some real life. This is real life. Does anybody want to guess how long it lasted? 72 hours. So it's the longest Legendre is out of the island. I have to go teach it before mine finished. So this is a very long example. Okay, so this is one way to think about when Legendrians are the same from this viewpoint of the phones. Okay, are we good so far? Okay, so what was I mentioning at the beginning of the talk? I was saying, well, there's these Legendrians in this contact 3 manifold. The contact 3 manifold bounds this symplectic 4 manifold. This T infinity, sorry, the star of R2, the infinity of R2 bounding the star of R2, just a standard symplectic variable 4 ball. And I want to study Lagrangian fillings of Legendre knots. For instance, if 2 Legendre knots have different Lagrangian fillings, that might be something that helps us. So a very interesting example in here is the following. And yeah, if you cannot see, please let me know. So this is a smooth representative. Smoothly, this is a knot that represents a smooth type, the mirror of 5-2. Let's call these guys lambda 1. And there's another way of representing the smooth type of M52, which is not so apparent from the front that you're going to get exactly the same knot. So let's right here. So smoothly, those two guys are the nope, they're not the same. There we go. So this is really simple to think about smoothly because all you have is 1, 2, 3, 4, 5 regions. Well, all you've done is you've taken the unknot, done ping, 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 twist it until you create 5 regions, and then you class them like that. And whether you count them as 1, 2, 3, 4, 5 versus 1, 2, 3, 4, 5, smoothly nothing has changed. Yeah. But interestingly, it's a beautiful theorem of Chekhanov, these guys are not the same. So smoothly the same, but Legendrian not the same. This was in many ways a foundational theorem of Yuri Chekhanov in 2000, starting the study of Legendrian knots as really a refinement of smooth knot theory, not just like, oh, it's smooth knot theory where you have this geometric thing, No, this is really telling you it's possible for smooth knots to be smoothly isotopy, but when I pick a Legendarian representative, there might be significantly different. And by the way, throughout these lectures, I'm completely going to ignore like formal stuff. So TV and rotation, I consider that part of sort of classical algebraic topology. So these actually have same TV, same rotation. We cannot be distinguished in that way. This is generally a refinement of sort of classical algebraic topology. Are we okay with that? Okay, so as I was saying, you care maybe about Lagrangian fillings, and that's one way to tell these two guys apart. So if you try to study Lagrangian fillings of this guy versus Lagrangian fillings of this guy, you start noticing differences, and that can be formalized. This day we talk about augmentations or generating polynomials or rolling polynomials, so on and so forth. But these will give you invariants telling you that that guy cannot be possibly a generous form. Because if this had a Lagrangian filling, then through an smooth isotopy, I could concatenate the Lagrangian filling with that Lagrangian concordance, and that will give me a Lagrangian filling. So essentially, the Lagrangian filling should be in the natural numbers. Does that make sense? Okay, so that's one motivation to Lagrangian fillings, just to tell the gender knots. Okay, so now how do you build Lagrangian fillings? Yeah, tricky business, but very, very beautiful one. So there's not a general set of rules that I know of, but at least in 3D, we have some number of versatile results that can help. So first comment, can somebody give me a Lagrangian filling of this guy into infinity of R2? Or recall that this is the fiber, isotopic to the fiber of the infinity of R2 into R2. It's a Lagrangian fiber. It is obviously the fiber, it's literally above a point, and you can deform it in other ways. So what is the Lagrangian filling of that? Just kind of the potential fiber of infinity of R2. So that guy bounds, this guy bounds a Lagrangian disk. It's a beautiful theorem and a non-trivial one, but actually this disk is unique. It's not possible to have any kind of interesting smooth knotting already happening. It's really the only Lagrangian disk. Okay, what about this one? So maybe a first intuition, at least for the left-hand side, is what am I drawing these? I'm drawing these in the Q1, Q2 plane. The Q1, Q2 plane is Lagrangian. So at least I have this smooth disk in here, which is in their Lagrangian, right? Now the problem is this lives in Q1, Q2. It doesn't kind of go up to the infinity of R2. With my hands to say, at least in this example, you can make that precise. You can take that disk, take the union with the cone of that boundary, and then smooth that out. That's not always possible, but in this case, it is possible. And that also bounds, so these both of them bound Lagrangian disks in a simplification of infinity of R2. Yeah. This guy, they all start to bound different things. So for instance, these two guys in here, I didn't say that, but from the theorem in there, really nice exercise, try to show that they are the same. These two Lagrangian knots are both max-Taylor representative of the right-handed trefoil. So they do bound and a Lagrangian torus, so Lagrangian once puncture. And all of these, which again, exercise from the theorem, check that they're all equal, they all bound a Lagrangian cylinder. So these you can kind of do by hand and with formulas. I've had to learn it, and it's doable, but it becomes very unfeasible. You want to have a more general theorem, which says, okay, here's how you build Lagrangian covariisms. So general Lagrangian fillings or Lagrangian covariisms via fronts. So this is what Arnold and company would call perestroikas of fronts and searchers in general. So the following moves on the front can be lifted. They can be upgraded in the 4D geometry to Lagrangian covariisms. So yield Lagrangian covariisms. And when you have a covariism down to the unknot, to the empty set, or the unknot, and then you fill with the disk like that, then you're done and you have a fill. So the first one is the fact that you can go from the empty to the unknot. You can think of that as the fact that these did bound a Lagrangian disk. So that covariism is going to have one minimum. Smoothly, it has one minimum in the direction of the simplification. The second one is, and there's going to be, I have to talk about orientations at some point. Second one is going to be, if I have two strengths like that, and for now, let me orient them this way, then you actually can go down and create two cusps like this. So orient this way. Okay. There is an unoriented version of that move, also a realized unoriented stuff. So this would be one saddle point in the covordism. And then there's other moves that you can do, some of which are deducible from these ones. So 1 and 2 are kind of the fundamental ones, and then there's 2 more, which is you could see here. Now this is what Arnold called the dangerous tangency, but these days we usually call it the class move. So suppose these both are oriented downwards, you could do that. That gives a Lagrangian covordism. But that is an immersed one, so I'm gonna write in red, immersed. There's nothing wrong with being immersed, by the way. I'll do a little rant on these in 2 minutes. It's fine to be immersed. The red is a choice for attention. It's not a criticism. And then you have variations on these moves. And as I said, one move that I find very useful and will use a lot during the lectures is the following: is like if you have this and you're like, I want to do a class move, but you're a bit worried about the immersed part, you can at least go down to 1. So 1 cross. And I'm gonna call this a D4 minus covordism. And I mean, we've studied it a lot in many ways. I like how James wrote it in one of his papers where he kind of explained geometry. And this guy is deducible from this guy. So you can try to realize these by doing these, and then a Rollmeister move, so on.
If you're okay with immersed covordisms, can't you go both directions on any of the moves?
So now will come the range of immersed stuff. So I'm not okay with immersed covordisms. I'm okay. So let's talk about it. So now, how do you go about building a Lagrangian fill? Well, you take any node you have, and now you can try to apply any of these moves. Sometimes you cannot, or it's not obvious what to do. And then you can do some isotopies. So in general, it is the combination of these 2 theorems. There's a reason why they're the same board, where what you do is you do possibly some isotopies, then one of these moves, possibly some more isotopies, then one of these moves, so on and so forth, back and forth, back and forth, back. And that's a way of building Lagrangian fill. So for instance, you could take these 2 crossings in here, apply the D4 minus, you're now down to 1 crossing. Now you're in this coupling. You could apply another D4 minus, go down to something that's going to look like this, like a Rollmeister 1. So now you're down to the unknown. So that's 2 saddle covordisms down to the unknown. A Lagrangian this, 2 saddle covordisms, that's a 1 puncture terms because it has connected them. As an example. Does that make sense? Okay, so little rant. Yeah, that means that you have to shut up, or no? Okay. So I like unobstructed covordisms. So fillings in general, but let's say covordisms. So and now the comment here is immerser. So okay, so let me maybe comment on this in the literature. So embedded covordisms, embedded Lagrangians, have the property that they're always unobstructed. Okay, what does unobstructed mean? There's no definition. It mostly means you can do whatever you're doing your days in a way that is well defined. So for instance, if you're thinking about floor theory, it means the VGA is well defined, like del square actually is 0. If you're doing floor theory, again, you actually have a chain complex, del squared equals 0, so on and so forth. If you're doing shift theory, it's about certain functors being defined, or the target category being isomorphic to some other more easier category, so on and so forth. But it mostly means that the geometry is very nicely reflected with invariants, and there's no obstruction to making those invariants well defined. Okay. Now, if you have an embedded filling, you're going to be unobstructed, like from a floor theoretical viewpoint and from shift theoretical viewpoint, so on and so forth. Okay. Now, the issue with immerse is that sometimes yes, sometimes no. So I feel sometimes there's some kind of allergy towards immerse fillings. Immerse is not the right thing to talk about, in my opinion. This is a personal viewpoint, but the right thing to talk about is about obstructive versus unobstructive. Whether you're immersed or not, I couldn't care less. I think that there's perfectly fine geometry, and I'll talk about that from a derived geometric viewpoint. If you think about a derived stack that I'll talk about at some point, there's essentially no difference between an immersed filling and an embedded filling. I get that, smoothly, you're like, oh, I really like embedded surfaces versus immersed ones. Doesn't seem to be an issue from a symplectic viewpoint. Symplectic and convex geometry cares about functions and their first derivatives. And they don't care whether it's inverse or not, and the theory is well defined as long as you have these unobstructed. So if you have immersed filling, the thing you have to worry about is, am I obstructed or not? Now, the class move, under certain circumstances, namely there's no handle slide here in the middle, so on and so forth, sometimes will give you immersed fillings which are unobstructed. So the class moves can be very useful for that. So for instance, when you think of generating functions, if you're familiar with that way of filling things, generating families, I would almost say tautologically are unobstructed because you have generating function homology. So now generating functions sometimes give you immersed fillings, that's fine. They're unobstructed, they still have a theory, that's fine. Does that make sense?
What do you mean by obstructed or unobstructed in this case?
So if you're thinking in terms of for theory, I mean that there is a well-defined augmentation for the DGA. If you think in terms of shift theory, it means that they can be shift quantized. If you're thinking of generating functions, it means there's a generating family generating quadratic and infinity. In linear infinity.
Yeah, like a simple example of a movie that gives an obstructed filling, like the most basic example.
Yeah, take this one and go bang, 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 bang several
Separate.
times. Separated, united, separated, united, separated, united. That's or anything. I mean, there are very strong constraints in the topology. So, for instance, something that distinguishes smooth topology from symplectic topology quite harshly. The unknown bounds a Lagrangian disk. Smoothly, it bounds a disk, and inside of it, you can keep adding genus, right? So you can do like genus 1, genus 2, genus 3. There's no problem with smoothly doing that locally. There is no other Lagrangian filling for the unknown, but actually, it's much simpler to prove that any Lagrangian filling ought to have the other characteristic of the disk, and so be it. Okay, so any Lagrangian filling of the trefoil must be a once-punctured toric. Now, it might be a Lagrangian different, but smoothly must be that. So any Lagrangian filling that you obtain, which has the wrong topology, say a genus 2 filling for the unknown or a genus 7 filling of the trefoil, gotta be obstructed. Okay, and you can build a lot of them. So the other side of the coin is that for immersed ones, there's Gromov-H principle. So the thing to be careful about here is, so the H principle of Gromov, it says that there's a lot of immersed Lagrangians out there, like, and they will typically obstruct. So it's not that you're hunting for any immersed Lagrangian, you're hunting really for the unobstructed ones. Are we good so far? Okay, so I'm going to do a quick summary of the lecture and then where we're going next. So what has happened? Okay, the ambient manifold is T infinity of R2 in our context setting, and in there we have Legendrians. So there's going to be Legendrian nodes, Legendrian links in our case. Now this T infinity of R2 manifold is bounded by a 4-ball, in this case T star of R2 with this particularly real symplectic structure, and we're going to care a lot about Legendrians that bound Lagrangian fillings. Now, questions, goals, you try to classify. So you try to say 2 Legendrians are different or they're equal. This boarding here allows you to try at least to show that certain Legendrians are equal and gives you tools to show that there are Lagrangian fillings and potentially build many candidates. So as with any classification problem, what you do is you produce tons of examples, say tons of Lagrangian fillings through these methods using these things. And then you're done with the first part, which is producing a lot of candidates. And then the second part is like try to tell them apart. And then you try to tell them apart as much as you can using some kind of invariant. And then part 3 is to claim that you're indeed done, which is when the invariants couldn't tell apart, then actually you go back to step 1 and try to show that they're equal. Not exactly. That's the third step is kind of hard. Okay. Okay, so what is going to happen through these lectures is that motivated by this geometric problem, we are going to study invariants of Legendrian nodes and their Lagrangian fillings. It will kind of come in one package. You can use it in both ways in order to tell Lagrangian fillings apart and in order to tell Legendrians apart. The way we're going to do it, it's just the choice is going to be this microlocal theory of sheaves. Okay, so in the second lecture today, I'm going to introduce what is a sheaf, what is a singular support, and give a hint of how that starts to connect with Legendrians and Lagrangians. And we're going to build from there. Okay, as I said very quickly, what, Len, you want to say something?
Yeah, your convention on that board is not that Lagrangian cobordisms are necessarily exact, right? So you should say that these are actually all exact.
Yeah. Yeah, so yeah, just, I really mean it like till 5:30 PM. I'm definitely available for you. Just come anytime, doesn't matter if I'm like drinking water, lunch, not the bad. Yes, but, you know, like, something reasonable, and then we can talk and about anything. I mean, very technical, or it can be just, why are you doing this? That's perfect. Okay, let's have a break.